Hey everyone, here we go with lesson 4.1. We're going to take a look at properties of square roots and radicals. So we're pausing here just for a little bit to step away from solving quadratics to take a look at properties of square roots, because this is going to be very helpful in the next couple of lessons where we go back to solving equations. So let's take a look. So in many instances, you'll see that understanding square roots and radicals are going to be very helpful when solving quadratic equations. So the specific properties of radicals. So a radical is an expression that contains a radical sign. So I think you've seen something like this before. An expression involving a radical sign with the index n is in simplest form when there are three conditions that are met. So number one, no radicands have perfect nth powers as factors other than one. No radicands contain fractions, and no radicals appear in the denominator of a fraction. So radicals are similar to exponents in that they can be written as an exponent, but the exponent would be a fraction. So let's take a look, zoom in here. The square root of x is the same thing. It can be rewritten as x to the power of 1/2. So the square root, the index, goes right here. But when we're just talking about the square root, we usually don't put 2, but we'll see that when we take the third root or the fourth root, we do include an index. So the position right here is called the index. So the index on a square root is 2. In this case, you can simplify perfect square numbers. Perfect square numbers like 1, 4, 9, 16, and then 5 squared is 25, 6 squared is 36. So it's a really good idea to have an idea of the first few perfect square numbers when we're dealing with square roots. Another example we have is the third root of x, and here the index is 3. So here what we're talking about is x to the power of 1/3. And cube root, now you're thinking of numbers. Well, what number times itself 3 times? That's a perfect cube number. So we have 1. So 1 times 1 times 1 is 1. We have 8. 2 times 2 times 2 is 8. And then 3 times 3 times 3 is 27, and so on and so forth. So since radicals are another way of writing exponents with fractional powers, the exponential rules that we reviewed before are very similar. So the first one is the product property. The square root of a product equals the product of the square roots of the factors. So in numbers, if I have the square root of 9 times 5, it's the same thing as finding the square root of 9 and multiplying that by the square root of 5. It helps us simplify because we can take the square root of 9, it's 3, and we'd have the square root of 5, which we can take on a calculator, but it would be a decimal, and it's just neater to leave it under the square root sign. Algebraically, if we take the square root of a times b, then that is the same thing or equal to taking the square root of a and then multiplying it by the square root of b. So where b and a have to be greater than 0. Okay? They have to be greater than 0 because you cannot take the square root of a negative number. Okay. Okay, let's take a look at simplifying some expressions. So if I want to simplify the square root of 108, I can start to split 108 into perfect square numbers. So the idea is to split 108 into perfect square numbers. And here is where it is helpful if you have an idea of perfect square numbers in your head. So we could split 108 into 4 and 27. And then we could further split the 27. So we could have 4 times 9 times 3. And then we can split each of these into its own square root. So the square root of 4 times the square root of 9 times the square root of 3. And that's the product property. Then we simplify, we have the square root of 4 is 2, and the square root of 9 is 3, and we have the square root of 3. So 2 times 3, we would simplify that to 6. And so my simplified square root expression is 6 times square root 3. This will get easier once you get the hang of it. So let's try the next one. Square root of 9 times x cubed. So looking for perfect square numbers, let's go ahead and split this into the square root of 9 times the square root of x cubed. Well, we know the square root of 9 is 3, but how do we deal with this square root of x cubed? Well, remember, x cubed is the same thing as x times x times x. And if I want to take the square root, remember this index is 2, what we do is we take one x out for each pair of x's that I find. So in this case, we have 3 x's under the radical sign, but we only have one pair. So I'll take an x out for that pair, and what's left over is a single x under the radical sign. So this is the simplified form of the square root of 9x cubed. It's 3x times the root of x. Again, we'll take a look at an example, the square root of 24. Let's start to split 24 into some perfect square numbers. Off the bat, I can think of 4. So 4 times 6. We can't split 6 into any other perfect squares. We can split it into 2 and 3, but those are not perfect square numbers. So let's go ahead and take the square root of 4 times the square root of 6. That's our multiplication or product property. Square root of 4 is 2 times the square root of 6. So that is our simplified. Over here, we have negative square root of 80. Let's start to split this up. We have the negative sign out here, and I believe 16 times 5 would give me 80. So that'll be negative square root of 16 times the square root of 5. Square root of 16 is 4. Don't forget that negative sign. It's negative 4 times the square root. I'm just going to put 2. Square root of 5. There we go. Take a look at E. Again, we can mix numbers with variables. So we can go ahead and split those up. Right away, I'd like to split them up. So the square root of 49 times the square root of x cubed. And the square root of 49 is 7 times, and I'll just show this to you again, x cubed is x times x times x. And since we're taking square root, that means there's an index of 2. Then I want to be able to pull out 1x for every pair of x's. And here I only have one pair of x's. So what I do here is I have the 7, and I pull out 1x for that pair, and I'm left with an x under the square root sign. So that's our simplified expression there. And then we have the square root of 75 n to the power of 5. And again, I'm going to go ahead and split this into the square root of 75 times the square root of n to the power of 5. And 75, that can be split into 25 times 3. Nice perfect square number there. And what I'm going to do here is I'm going to expand all of these n's. N to the 5 is n times n times n times n times n. So I have the square root of 25 times the square root of 3. And remember, we were talking about the index being 2 when we have square root. And so we're going to take out an n for every pair. And in this case, we happen to have 2 pair of n's. So we're going to pull out 1 n for each of those pairs. So simplifying, square root of 25 is 5. And I have the root of 3. And then I have an n for 1 pair and another n. And then I have the square root of 1 n that's left over. Well, this looks like a mess. Let's go ahead and tidy that up. We usually bring out coefficients. So the 5 n squared, we're going to put that all together. So that's this 5 and these 2 n's go at the front. And then we have the root of 3 times the root of n. And we might as well go back and put those back into our square root. So it looks neater, square root of 3n. So those are all dealing with the product property. Let's take a look at the quotient property. So the square root of a quotient equals the square roots of the numerator and the denominator. So the square root of 3 divided by 4 is equal to the square root of 3 divided by the square root of 4. Then we can simplify top and bottom. So a has to be greater than or equal to 0 because we can't take the square root of a negative number. And b has to be greater than or equal to 0 because two things, we can't take the square root of a negative number and we cannot have a 0 in the denominator of a fraction. That's undefined. So let's go ahead and try and apply this to some examples. If we simplify this expression, the square root of 15 divided by 64, we can split this by the quotient rule into the square root of 15 divided by the square root of 64. And then the square root of 64 is 8. So this just simplifies to square root of 15 over 8. I couldn't think of any other perfect square numbers that 15 can be divided in, so it's just going to have to stay that way. Next, we have the square root of 81 divided by x squared, and we can split that up into the square root of 81 divided by the square root of x squared. And this simplifies. The square root of 81 is 9, and the square root of x squared is just x. Moving on to some further examples. We won't work too much with cube root, but it's some good practice. So using properties of cube roots, so you can extend the product and the quotient properties of square roots to other radicals such as cube roots. When using the property of cube roots, the radicand may contain a negative number because if you cube a negative number, you will get a negative product. So let's take, for example, if you take -2 and you cube it, -2 times -2, you will get a -8, a negative product. Therefore, you can take the cube root of a negative number. And this is going to go back and give you -2. Let's keep that in mind. So when we're dealing with cube roots, you will always see the index is 3. So we have a negative number, and we can take the cube root of a negative number, and let's start to split that up. Think 128 can be equal to the cube root of -64 times 2. I can take the cube root of -64, and that would be -4. And that would leave the cube root of 2. So I have -4 times the cube root of 2. And that's how we simplify that first example. The next example, cube root of 125 times x to the power of 7. So let's go ahead and split the numbers and the variables. Let's take the cube root of 125, and this is the product property, times the cube root, and I'm going to put all of them. Here's my cube root, x times x times x is x, 1, 2, 3, 4, 5 times x, 6 times x, 7. So there's 7 of them. Now, here, since we are taking the cube root, we want to take out an x from the radical for every 3 sets of x's. The last example, when we were taking the square root, we wanted to take out an x or a variable for every pair. But now, because we're finding the cube root, we want to take out an x for every 3 sets of variables. So the cube root of 125 is 5. And then we'll take out an x for those 2 sets of 3 x's. So x and another x. And I'm going to be left with the cube root of the single x that's left over. Go ahead and tidy these up. And I'll have 5x squared times the cube root of x. Working again with the cube root, quotient property, we'll split this into the cube root of y divided by the cube root of 216. And we cannot simplify the numerator. That will have to stay as the cube root of y. And the cube root of 216 is 6. Okay, another example where I have numbers and letters. Let's split up the top and the bottom. We'll take the cube root of 8 times x to the power of 4 divided by the cube root of 27 times y cubed. I'm going to go ahead and expand across the top and separate. So we have the cube root of 8 times the cube root of x times x times x times x, all divided by the cube root of 27 times the cube root of y times y times y, y cubed. Again, we are looking for the cube root, so we're going to take out a variable for every set of 3. The cube root of 8 is 2, and then I have one set of 3, so I can pull out an x, and I will have the cube root of x remaining. In the bottom, I have the cube root of 27, which is 3, and I can take out a y, and I have one set of 3 y's, so the cube root and cube cancel. So I pull out one y here. So that one, we're going to take a look at one more thing that's really important when we go back to solving our quadratic equations, and that is something called rationalizing the denominator. So when a radical is in the denominator of a fraction, you can multiply a fraction by an appropriate form of 1, because if we multiply by 1, we don't actually change the value, but it does help us to eliminate the radical from the denominator. And this process is what we call rationalizing the denominator. So let's go ahead and start with this example. If we have the root of 5 over the root of 3n, if you recall the 3 important factors for radicals, no radicals should appear in the denominator. That's when we know that it is in simplest form. So here we do have a radical in the denominator. So watch the process. What we do is we multiply by what's in the denominator over itself. because this, the root of 3n divided by the root of 3n, is really equal to 1. So we haven't changed the value of the expression. But what that does do is it allows us to get rid of these two root signs, because the square root of 3n times the square root of 3n, that's just going to simplify to 3n. But on top, we have the square root of 5 times the square root of 3n, and we have the product property, so we can go ahead and just write that as square root of 15n. Let's take a look at a different example. So we have the 2 divided by the cube root of 9. 2 divided by the cube root of 9, we rationalize the denominator by multiplying the denominator over the denominator. So the cube root of 9 over the cube root of 9. Again, cube root of 9 divided by the cube root of 9, that's equivalent to 1, and so it doesn't change the value of the expression. And what that does is it gets rid of these cube root signs. So I will have 2 on the numerator times the cube root of 9, all divided by 9. Can't really simplify anything more than that, so we leave it just like that. And the next thing we want to do is just take a look at some performing operations with radicals. So radicals with the same index and radicand are called like radicals. So you can treat them just like terms when we're simplifying other polynomials. So you can add and subtract like radicals the same way you combine terms using the distributive property. So let's take a look. We have 5 times the root of 7 plus the root of 11 minus 8 times the root of 7. So what this means is, since this square root of 7 and the square root of 7, they have the same index and they have the same radicand, which is the number underneath, we can go ahead and combine 5 with negative 8. So that gives me negative 3 root 7. But the square root of 11 is not similar to anything else, so that stays square root of 11. Taking a look at B, we have the same index, but it doesn't really look like we have the same radicand. We have 5 there and we have 20 there, but we can simplify the square root of 20. So I'll rewrite 10 times the square root of 5 plus the square root of 20 can be split into 4 times 5. So we'll have 10 times the square root of 5. And I can pull out this 4. I can take the square root of 4. And so I will have a positive 2 square root of 5. Now I do have the same square root, and so I can combine them like terms. So 10 square root 5 plus 2 square root 5 is 12 square root 5s. Okay, so let's take a look at expanding a little bit here. Remember our product property. So we have the square root of 5 times bracket square root of 3 minus the square root of 75. And essentially what we do here is the distributive property. And we'll have the square root of 15 minus the square root of 5 times 75 is 375. And square root of 15 can't be simplified, so I'm going to leave that as the square root of 15. But we can start to pull apart that 375, and the first number that comes to mind is 25 times 5, times, I checked that on the calculator, it's actually times 15. And then I have the square root of 15 minus square root of 25 is 5, but again, I can't take the square root of 15. But now I do end up with the same square root the index and the radicand. And so I can combine, this is like 1 root 15 minus 5 root 15, and I end up with -4 times the square root of 15. And one last example, I'm going to throw in some variables with this one. We're still going to use the distributive property and keep an eye on how this develops. So 7 times 27, I'm going to get the square root of 189. And then the y times the y, that's going to give me y squared. Plus 5 times the square root of 7 times 12, which is 84, and y times y, which is y squared. Start to split this into some perfect square numbers. 189 can be split into 9 and 21. And then we have 2 y's plus 5. 84 can be split into 4 and 21. And then we have 2 y's. And we can take the square root of 9. That's going to be 3. We cannot take the square root of 21. But remember, the square root, we can take out a variable for every pair. So I'll pull out a y. And so I leave the 21 under the radical sign. Moving over 5 times, I can take the square root of 4. And that's 2. And I can't take the square root of 21. But I can take the square root of this pair of y's here. So I'll pull out a y. And what's left is the square root of 21. I'm going to tidy this up a little bit right here. And I have 3y times the square root of 21 plus 10y times the square root of 21. And when I combine those, I will get 13y times the square root of 21. Okay? So that is a lot probably for practicing with square roots and radicals. But again, it's important to know this because going forward into the next few lessons, when we are working with solving quadratic equations, the square root is really important. So go ahead and practice on your worksheet. Let me know if you have any questions.